Today we're going to start talking about the first chapter under association-based claims, and that is about bivariate correlations and research involving them. So we'll jump into bivariate correlations. A bivariate correlation is the association or correlation between two variables. If you have more variables, you can run correlations, but then it is multivariate correlations or associations that you're looking at, not actually bivariate any longer. When you're looking at bivariate correlations, this is just a way to establish or rank them in terms of small, medium, and large. So a correlation coefficient of 0.1 to 0.3 is generally considered small or weak. A correlation coefficient of 0.3 to 0.5 is generally considered to be medium or moderate. And a correlation of 0.5 all the way up to 1 is considered large or strong. Note that the same magnitudes apply for negative correlations, such that negative 0.1 to negative 0.3 would be a small correlation, and negative 0.5 to say negative 1 would be a large correlation. Some examples that are in your textbook that you can look at visual representations. Here you can see the relationship between how much substantive conversations, sort of how deep conversations people have, seems to be correlated with happiness. I'm just going to turn on this pointer. So here you can see well-being scores have been transformed into z-scores on the x-axis, and the percentage of deep conversations that people have is on the y-axis. So the well-being is measured with the subjective well-being scale, and the amount of deep talk was measured by giving people recorders that turned on for 30 seconds every 12.5 minutes, I believe. And then the conversations were rated by the researchers to establish whether those conversations were deep or not, and what percentage of their conversations were ultimately deep or substantive conversations. And then they correlated these two things. You can see here they're showing sort of this best fit correlation line. And even though it does look somewhat like a cloud of gnats, you can see that there is a probably small to medium correlation that exists with this data, such that the increased well-being, the more substantive talk people are having. I will say this a couple times throughout this lecture, but please note that you cannot ultimately express directionality from just a correlation. We do not know if people who are higher on well-being have more substantive conversations, or people who have more substantive conversations are just higher on well-being. It could technically go either way. Another one presented in your textbook here is people who multitask tend to be worse at it. We've seen this before in a previous chapter. This was operationalized by asking people to report how many hours they spend on different forms of media and how many of those hours they spend on multiple forms of media. So for example, how many hours of television does one watch, and how many hours of social media does one engage in, and how many hours does one do both. And then it was, or actual multitasking capabilities was measured using this OSPAN score, which is just an operation span task, which has you remember a series of letters while you are solving mathematical equations in your head, and you have to be able to report the correct answers of the math equations. They're generally relatively simple arithmetic, but while you're doing that while also trying to remember a stream of letters, it tends to be pretty difficult. And here, I guess you can, if you look at the data, you can see there is somewhat of a negative correlation, though this too again is probably not very strong, as you see data sort of represented all across this map. This is one of the reasons why ultimately calculating correlation coefficients is important, above and beyond simply looking at your data. Even though I highly recommend looking at your data, you should always look at your data. I mean, you shouldn't peek at it before you have your complete set, but you should always look at your raw data to make sure nothing is funky is going on. And we will talk about something called exploratory data analysis towards the end of this lecture. And it is just a good practice to have. Many people have often gotten in trouble for not adequately checking their data before willy-nilly running a bunch of statistical tests on it. Finally, you can also have correlations when one of your variables is binary or categorical. So in this case, they're talking about partners' marital satisfaction is related to whether they met online or in person. And so here you can see on the x-axis, they are either they met online or they met offline. And here is their marital satisfaction. And so here you're just seeing a group of people. These are all of their marital satisfaction scores, and they all met online. Same thing for those who went offline or met in real life, I suppose. And if you were to try and draw a line between these, it might not be intuitive at first if this is not something you have done before, but if you were to pump this into a statistical program, it would draw a line with a slight negative slope, ultimately between the two means of both of these groups. Another thing just to keep in mind, sometimes correlations in which one of your variables is binary is often called a point biserial correlation. Now, this data could also be represented as so. Here you see ultimately the same data represented, except here online and offline are again on the x-axis and marital satisfaction is again on the y-axis. And the only difference here is we have two bars representing the averages of both groups. And this actually does make it a little bit easier to see that people are slightly more happy when they met online as opposed to offline. Now, of course, again, you cannot say that meeting online is likely to lead you to have higher marital satisfaction. One just doesn't know that yet. There could be other extenuating factors that are leading to people in this online condition having higher marital satisfaction. For example, let's say people who are more committed to relationships, they could spend more time online looking for potential spouses or partners, as opposed to someone willy-nilly moving throughout their life and they're just sort of ad hoc seeing if they meet someone they care about. And so maybe those people who are more looking for a relationship and thus tend to spend more time online also tend to work harder at their relationship and thus have slightly higher marital satisfaction. Ultimately, we cannot make directional claims with these types of data. The reason I'm bringing this up here for this set is, one, it is possible to have correlations where one of your variables is not continuous, that is represented here, and two, whether your data is represented as a bar graph or a scatter plot does not tell you that much about what type of claim is being made. Ultimately, for that, one needs to look at what the hypotheses presented by the researchers are and what their methodology was. Okay, talking a little bit more about correlational studies. So any study in which both variables are measured is technically a correlational study. So even when one is running an actual experiment in which you are manipulating one of those variables, you are still measuring both of those variables, and a correlation coefficient can be calculated. Now, oftentimes one has many times heard, and maybe I've said this in class before, but we often hear correlations do not imply causation, and that is really something to take heart. But there is the converse of that, of do causal paths ultimately imply a correlation? And yes, they do. In order for there to be a cause and effect, you have something causing something else. And whenever it is present, it causes the other thing. And when it is absent, it fails to cause whatever it normally causes. And that ultimately is an association. When it's present, you have something, and when it's absent, you have a lack of something, much like the previous sort of binary set of data I showed you for marital satisfaction and whether people met online or not. Along this, it is important to remember that association or correlational claims are not tied to any particular type of graph or statistic. So I mentioned this already with the graphs earlier, where I showed you a scatter plot, which is commonly associated with these type of relational claims, but it could have been represented on a bar graph as well. So there's oftentimes some confusion when it comes to these types of claims and when people see data. So oftentimes when people see Pearson's R coefficient, they tend to think, oh, there was a correlation and it is an association-based claim being made. And if they see the results of a t-test, they will often say, ooh, it's a two-group comparison and must have been an experiment, and so I can fit under a causal claim umbrella. That is definitely not the case. It turns out actually that you can interconvert between R and T. So this generally will only work for two groups. So either you have a relationship between two variables, or you're looking at the difference between two particular groups along a single other variable. And just in case you're interested, here are the formulas to convert backwards and forwards. So T is given by R squared times the degrees of freedom divided by 1 minus R squared, and you square root the whole thing. And to get your correlation coefficient from a T value, you can take the square root of T squared over T squared plus the degrees of freedom. Ultimately, these are interconvertible because most of the math used to derive either one of these statistics comes from the sums of squares, and the sums of squares is common to both of these statistics. The point of all that is just seeing a certain type of statistic does not tell you what type of design was made, and it is important to keep track of that because it could mean the difference between saying two things are simply related versus if you take part in this, it will cause something else. And we will talk a bunch more about that towards the end of the lecture. So when it comes to interrogating association claims, basically what we mean here is we're going to look through how we can establish validity along the different metrics we have been talking about association claims. So first of all, questions about construct validity. Please just take a moment to refresh that construct validity refers to how well some measure that you have actually reflects the variables that are being measured. So if you have some metric that's meant to measure well-being, you're hoping that whatever results or data you get from this measure allow you to accurately predict people's actual well-being. If it does not allow that to happen, then this measure has low construct validity. If you have low construct validity measures in your study, it ultimately reduces the overall construct validity of that experiment. So some questions to ask in this vein of, did the measure have good reliability? Oftentimes people will report the reliability of measures. Sometimes you will have to go dig it up in other literature. Another is it actually measuring what it's supposed to measure? This is kind of the example I gave about well-being just a moment ago, but are your measures accurately reflecting the real-life phenomena that they are supposedly measuring? If not, they might ultimately be measuring something unrelated that you happen to think is this, and based on that, one can make all types of relational claims about variables that are not in fact actually related. Finally, are there evidence or is there evidence to support the different subtypes of construct validity? By this I just mean, is it face valid? Does it look like it measures what it's meant to be measuring, so long as it doesn't involve active deception and not just based on what we think, but have experts said so as well? Further, is there evidence for its concurrent validity? So basically the example about subjective well-being was talking about this. Is there evidence that the results from a certain measure accurately allow us to make real-life predictions out in the world? Does the measure actually measure what it is supposed to be measuring? Finally, is there evidence for either discriminant or convergent validity? This is talking about, does this measure accurately correlate with other variables that are logically related to it? And is it unrelated to variables that it is logically not at all related to? When it comes to questions about statistical validity, here this plays a much bigger role over previous claims that we have looked at. Really, those are just frequency claims, so this is the next one, and it plays a big role here. Statistical validity just refers to how well the data support a particular claim and how were the analyses actually conducted. Meaning, did people check their assumptions? Did they look at their data? Were the tests that they conducted appropriate? So on and so forth. And so over the next few slides, we will talk about effect size and how this relates to correlations, whether a correlation was statistically significant and what that means. And finally, was some type of exploratory data analysis conducted before conducting your actual inferential statistics? And we'll talk a bunch more about that in a few slides. Okay, so when it comes to effect size, there are many different forms of effect size when it's sort of broken down across the field of statistics, and almost always effect size is just a measure of the strength of a relationship or difference. One of the common ones that you probably have come across so far are D effect sizes, which refer to sort of how far the centers of two distributions are. Many times correlation coefficients themselves can often be used as an effect size, and ultimately that is because they are indicating what is the degree to which two things are linearly associated. More common than seeing simply the correlation coefficient, you will see R squared. R squared comes up a lot in regression models, but one will see it sort of all over the place. It's found just by taking the square of your correlation coefficient, and what R squared refers to is how much of the variance in one variable can be explained by another variable. So if you take, for example, you find a correlation coefficient of 0.5, And so you square this, you get 0.25, and you can convert that proportion now into a percentage, and you could say something like variable x is able to explain 25% of the variance of variable y. Meaning, if you know the actual values of a person or being or thing or whatever it happens to be on variable x, you can predict how much variability will be in those people or individuals on variable y, at least 25% of that variability. The rest could be explained either by other variables or just random error, and that's ultimately why many people, especially in regression, build models with multiple variables, because then your R squared is ultimately telling you how much of the variance in your outcome variable is predicted by all of the variables that you use. We'll talk about that more in the next lecture. Okay. Why does this matter? Well, larger effect sizes allow us to make more accurate predictions. So if you think about what I was just talking about with the R squared, as my correlation coefficient is higher and higher, as it approaches 1, the amount of variance explainable by one variable onto another approaches 100%. It of course takes a long time, and in real life we rarely ever find relationships that high. But ultimately, the higher that effect size, the stronger the correlation itself is, the more accurate predictions we can make based on the data that we have. If you just sort of think about it kind of like this, where you have two variables that are correlated at a very small correlation, let's say 0.1, and you look at what the data looks like, it will ultimately look kind of like a cloud of gnats, such that at medium levels of variable x, you can have high and low values for variable y. In that case, probably cannot make very good predictions. Versus if variable x and y are correlated at, say, 0.9, the scatter plot is going to look very close to a straight line. And in that case, when you try and make predictions based on one variable onto the other, your accuracy is going to be pretty high because you know that it exists almost on an exact straight line. Now, your book says, and you'll often hear this a lot, that larger effect sizes are more important. And I would take this a little bit with a grain of salt. A lot of the reason we say they're more important is because they allow us to make more accurate predictions. That is really the primary reason that larger effect sizes are important. Now, it is an okay rule of thumb to follow, but please remember that they are exceptions. Sometimes even a small effect size is very, very valuable. Imagine different types of medication. Your textbook uses aspirin for an example, but these cases are very common actually in the medical industry. And even if I have a very tiny effect size, something, let's say an R squared of 0.03 or something like this, very, very tiny, but I'm now looking at an entire population of hundreds of millions of people across an entire set of countries, let's say, and I know that providing a medication is going to slightly reduce the chance of some kind of illness, even though the effect size is very, very small, that over millions and millions of people can add up to quite a few people. And so if your new medication allows you to save an additional 10,000 people out of the million people who die of like coronary disease every year, even though that is a small effect size by comparison to others, it is a very meaningful difference, and in those cases it matters a lot. So do not just judge effect sizes by their size itself, but the context in which those effect sizes are embedded is just as important. This is oftentimes why, instead of just using those original criteria that I showed you earlier, which were actually put forward by Cohen, if you'd like to look into that more, you're more than welcome to, it depends a lot on the field you are using. You might find very high correlations in some fields of psychology and very low correlations in others, but if they are pretty standard for what is found in that field, they will generally be other benchmarks used by those particular researchers. Okay, when it comes to correlations and statistical significance, here we're talking about significance referring to the likelihood of finding a particular correlation coefficient given that there is no actual relationship in the population itself. So This is, of course, the logic of null hypothesis testing. We don't actually know whether there is a relationship in the population or not. What we're ultimately doing is deriving a probability value of what is the likelihood of finding a correlation that we have, or a more extreme one, if there was no relationship in the population itself. So basically, if you were to think about the standard normal distribution around z-scores, most of them show up around 0, which is what we would expect also for correlation coefficients if there was no relationship in the population, right? If the true R of a population was 0, we would expect our samples to have some noise, of course, because they're samples, and so we should get correlations that are sort of evenly distributed around 0. Of course, sometimes our samples will show some bias for whatever reason, and sometimes we will have more extreme correlation coefficients. Not necessarily that they need to be huge, but just moving away from that 0 value, either in positive or negative directions. And that proportion that we get ultimately is modeled to show how many times out of, say, 10 million repeats of that study, when no relationship exists, would give you correlations of certain sort of significant sizes. And the probability associated with each one of those is what is given by the p-value that you so often see in academic research articles. Okay, when it comes to significance, though, let's say you find some significant correlation. You get a correlation, let's say it's 0.47, and the p-value that you get is less than 0.05, so you become really excited because that means it's significant and publish-worthy. We won't get into that really here, but anyway, just because you find a statistically significant correlation does not allow you to know for sure that there is such a relationship in the population. You could say that the probability exists that it is true in the population, because if it was not, there is a very, very low chance that I would have found the correlation I found. But please note that it just says that there is a very low chance, not that there is no chance. This is one of the primary reasons why replicating our work in such endeavors is so important. Because while one time you might have a random extreme value, it is much more unlikely to have random extreme values over and over and over. If you were continually getting values that would look extreme if there was no relationship in the population, and it continues to be found reliably so, then we begin to make the inference of, this relationship probably exists in the population. Please remember though, cannot ever really know for sure. We just make our inferences more and more probable, would be a good way to look at it. Conversely, if you find a correlation that is not statistically significant, your p-value is now over 0.05 if that's the threshold you're using, you cannot make claims based on this null finding. Just because you did not find a correlation coefficient that was significant does not allow you to say that no relationship exists in the population. All it allows you to say is that this time you found a correlation coefficient that you could have found by chance at some proportion that is not below the threshold that you set. So a good way to sort of just think about this would be to think about the difference of a significant and an insignificant or not significant correlation when the p-values are very, very close. Imagine you find a correlation coefficient of something and the p-value with it is 0.049. Technically, you would reject the null hypothesis in this case. You would have a significant finding and you could talk about it in a journal. Let's say your peer conducted the same experiment and they found some correlation coefficient, but their p-value is 0.051. Technically, they no longer have a significant correlation, but what really is the difference between saying the chances of finding this correlation by chance alone for the first one was 49 out of 1,000. For the other one, it was 51 out of 1,000. And what really is the difference between 49 out of 1,000 and 51 out of 1,000? Hard to really come up with a good reason why those two things are different, even though our boundary for statistical significance and thus in a lot of cases publish-worthy articles is that small. That is our boundary line that exists for yes and no. So it's just important to know that ultimately all we're doing is making inferences, and p-values just allow us to say this is the probability of finding whatever difference we found or whatever relationship we found by chance alone if no actual difference or no actual relationship existed in the world itself. This is why ultimately all of this is about inferences, and we cannot ever really make hard claims about we guarantee this exists in the population unless you can measure the entire population. Finally, a little bit about sample size and statistical significance. So correlations, well, really ultimately any type of statistical significance test can be biased by sample size. So if I have 100 people in a study, I am unlikely to find a correlation coefficient of 0.18 as significant. While if I run exactly the same study, find exactly the same correlation coefficient, but this time I had 500 people in my study, that correlation coefficient is going to be tagged as significant. Now, overall, this works quite well in moderate or medium sample sizes because just think about it in this way of chance more heavily impacts small samples than large samples. I could have an extreme set of 5 people. That is probably more likely than finding an extreme set of 500 people if I'm assuming I found both sets by chance. Now, that is probably one of the reasons the math was set up as it was set up, but it was set up in a time where it was never expected to have thousands and thousands of people in the studies. Whereas now we can do that with online platforms and polls and these types of things. And it is possible to have so many people in a sample that even trivial differences, at least statistically, appear significant. This is why it is so important to understand what statistical significance actually means and not just use this threshold boundary for is it meaningful or not based on an ultimately arbitrary proportion value. Because not all fields use 0.05. Not all psychologists use 0.05. Right? It is context dependent. But it is really important to know that it is linked also to sample size. And unfortunately, one of the problematic behaviors that sometimes arises in this scientific field will be that someone finds a p-value on some study or dissertation that they were working on that is just really close to that 0.05 threshold, and instead of scrapping it or doing the study again, they'll just run an extra 15 or 20 people, or worse yet, run until their p-value becomes significant. Unfortunately, this happens more than you might think. Okay, so now a little bit about correlations and exploratory data analysis. It's often abbreviated as EDA. So exploratory data analysis is ultimately the analysis we do before conducting statistical tests. So it generally is related to understanding and getting a summary of our raw data itself. So oftentimes ways in which people go about this is they will make scatter plots or bar plots or box plots, let's say. Those are really important. They get used a lot in this. You could calculate means and standard deviations, establish whether your data is skewed or kurtotic, or does it approximate normal, or does it have some different type of distribution? And all of these things are important to know before you run your statistical tests, because many of our statistical tests have certain assumptions in what the data should be like for them to work properly and the proportion values that they spit out to actually be meaningful. A lot of times, it's again sad to say that people just don't check their data before running their actual analyses, because for many people, the actual analyses are just much more exciting than going through the actual data itself. But some specific things to keep in mind when it comes to correlations, probably one of the biggest is, are there outliers present? And this matters much more when you have a small sample size than a very large sample size, but it generally is a good thing to keep in mind. It's still on. So in this, these two are ultimately the same sets of data, except A shows an outlier over here. You can look through the book for the exact numbers, but I believe the correlation coefficient here is 0.56 and the correlation here is only 0.34. And the only thing that changed is one extreme value. So extreme values, or outliers in this case, can tremendously bias the size of correlation coefficients. And it's really something you want to watch out for. Now, it matters less the more and more people you have, that just intuitively you can think it through, that the greater number of people I have, the less likely one extreme person is to sort of change the overall outlook of the group. But when I have a very small subset of people, then a very extreme person is likely to change the overall outlook of the group, if I could take averages of outlooks, I suppose. So one really good thing to keep in mind is to check your data for outliers before you run your correlational tests. Two common ways that gets used. So you can, of course, just look at it via a scatter plot. You won't always find them, and sometimes it can be difficult to know. But in those cases, you're probably pretty okay anyhow. But if you wanted to conduct a sort of rigorous test to establish what are outliers and what are not, one, we oftentimes use box plots. And box plots are designed such that they have these two sort of cutoff bars, and those bars are 1.5 times the interquartile range above and below the 25th and 75th quartiles respectively. And if that made no sense whatsoever, technically you probably won't need it for this class itself, but I highly recommend looking up Tukey's box plots and how to use them to establish outliers, as it is a pretty standard way that gets used. The other common way you'll probably see a lot is any value that is more than 3 standard deviations away from the mean oftentimes gets labeled as an outlier. Now, there are many ways to deal with outliers, and many of those are going to be lab specific, and unfortunately people fight over which are the right ones to use all the time, and I'm not really going to get into that here in this lecture. Note that there are many ways to deal with outliers, and not all of them involve deleting your data though, and if you want to preserve your data exactly as it was, there's an entire branch of statistics called non-parametric statistics that will allow you to conduct tests on data that is not ultimately normal. Not normal in the sense of like it's weird, but normal as in it doesn't approximate the normal distribution. Okay, another thing to look at here is there some type of restriction of range? So you won't always see this in the data itself, even though it can be found there. A lot of times this can be found in the methodology that one is looking at. So restriction of range refers to, is there a certain portion of possible scores that could have existed that you are either not getting for some reason or you're choosing not to look at? So here you can see this top bar represents an actual restriction of range where only data for people with SAT scores above 1200 to 1600 are represented, whereas here you can see a full set of distribution scores where everybody with from 400 all the way to 1600. So this is talking about a university that is trying to ultimately defend their research policies. And here you have this sort of their line for they don't admit anybody with SAT scores underneath this, and then how they did in their 4 years of college. And so here you can draw sort of a relationship between these. I think this is again about a 0.3 relationship. So they're like, okay, yeah, look, as our SAT scores tend to get higher, so too does college performance. And now if you were to look down here, technically you can say that same story, that as your SAT score increases, your overall performance in college tends to increase as well. And here you actually will have a stronger relationship. So the reason this matters a lot is you will not always have the same relationship across all parts of your measured variables. For example, the relationship between SAT performance and college grades here could be quite different than it is here. And that can be problematic for many ways, and we'll talk about one of those in the next bullet point that I'm going to talk about. But the good thing to keep in, well, I don't know if it's good, but the thing to keep in mind here is that oftentimes when there is a restriction of range, when there is some type of artificial compression or ignoring of some aspect of your data, this will tend to suppress the value of your correlations, making it seem like the relationship is not as strong as it actually may be. Generally speaking, if you are in the pursuit of trying to understand what is going on in populations at large, arbitrarily selecting your data just to prove a point is probably not great policy. Times where it is actually defensible to look at small subsets of your data is when you suspect that different subsets of your data will have different types of relationships, and you would like to talk about how those different subsets are different. In those cases, it is defensible to look at subsets, but I would also argue that you might not then call it restriction of range, because overall you will still look at the entire range of your data. Finally, is the relationship itself linear? So linear relationships are ultimately relationships that approximate a straight line of some kind. Correlations are tests of linear relationships. They don't test other types of relationships. So this one here, for example, would be called a curvilinear relationship. You could also probably call this a quadratic relationship because of this shape. By that I just mean it approximates the shape of an x squared graph. There are, of course, all different kinds. These polynomial relations ultimately then get talked about as their orders of power. So if I had a relationship that kind of went down like this, then came back up, and then curved back down like that, that would ultimately be like a third power relationship. There are other ways to test for relationships of this kind. A standard correlation is not one of them. But you can't really know this unless you actually look at your data, and if you try and run a correlation on this type of data, your computer will spit out a value. And so data like this would actually ultimately represent a correlation that was pretty much flat, and you may conclude, ultimately incorrectly, that there is no relationship between these two variables. While, however, there is one, it's just not a linear relationship. So in this case, how old you are being related to how much one uses the healthcare system. Knowing that as very, very young children, we tend to go to the doctor a lot, and then throughout our teens, 20s, 30s, and 40s, we don't use it so much. And then as we get to these riper, older ages, we tend to use the medical care system much more. And this is a pretty solid relationship, even though a correlation on this would give you a very small value, leading one to conclude that there is maybe no relationship between these two variables. You don't need to know off the top of your head how to analyze all of these. Ultimately, you can look these up if you're ever going to go into this field, and the more you use them, the easier it will be to come across them. Your book does mention that you can run a correlation on the values of one while taking the squares of the other. I personally have not heard of this method being used, so I cannot comment one way or another. Okay, questions about internal validity. So internal validity is not the biggest focus when it is coming to associations. Remember, please, that internal validity refers to how well we controlled for alternative explanations. That oftentimes is being used when we are talking about one variable causing another. When we're making a claim that is causal, we're saying something led to the effect of another, and we are now trying to mitigate alternative explanations that could also be used to explain why we're seeing the difference in whatever our outcome variable is. Now, something that is very important in this regard is to be very, very, very mindful not to just make causal claims based on association or correlational data. And this is very, very common. Not only does it happen in media and stuff like that, but we will see it in our own language as well. It is often easier for us to communicate in causal terms than correlational or associational terms. We also tend to have somewhat of an aversion, just at an intuitive level, to speaking in terms of simple relationships as opposed to causal structures. At the end of the day, we like talking about things in causal structures, and it is important to be very mindful that based on these types of claims, one cannot make causal statements. In order to make causal statements, we will talk about the three things that you require now. So the first is a covariance of cause and effect. This is ultimately what we've been talking about this entire lecture. Is there a relationship between the two things that you think have a causal relationship? So if I have the idea that if I knock over a young child's ice cream, that they will begin to cry, I am making some type of prediction that there is a relationship between a mean bully knocking over your ice cream and a young child crying. Now, when there's the mean bully knocking over the ice cream and they cry, there's the presence of their cause and effect are both present. But when I don't knock over the ice cream and they don't cry, in this case, cause is absent and effect is absent. In this case, they're both co-varying. They go together. Both the positives are together and the negatives are together. Of course, it could be flipped, right? Where, let's say I knock over the ice cream and they laugh, and I don't knock over the ice cream and they cry. In that case, there is still a covariance of cause and effect. It's just in the opposite direction. You can see that represented sort of here is just, is there a relationship between A and B? There must be a relationship between the two things that you would like to make a causal claim about. If there is no relationship, if there is no correlation, you cannot make causal claims. Next is temporal precedence. This is basically talking about the order of time. Did the variable that you suspect is the cause come before the variable that you suspect is the effect? You cannot have an effect that comes before the cause. That just doesn't make sense. This is oftentimes called the directionality problem, and you cannot have effects that cause the cause. That just doesn't make any sense, right? The crying doesn't cause the bully to drop the ice cream, so to speak. It's when the ice cream is knocked over by the bully, the kid starts to cry. It's not that whenever a kid starts to cry, a bully magically shows up and knocks over their ice cream. That would just be kind of strange. I mean, maybe it could happen in a strange alternate reality, but probably not. Okay, when it does come to internal validity, so oftentimes what we would talk about here in terms of associations or correlations is there some other variable that could explain the relationship? And by this we mean, is there some other variable that is correlated with both of the two variables I tested in such a way that the correlation between them is not actually reflecting the relationship between them, but it's reflecting the relationship of how both of those two variables are related to some as yet unmeasured third variable. You can see that sort of represented here, where A and B are technically correlated to each other, but not because they are related, but rather because both are related to some other variable. We'll talk about this a little bit more on the next couple slides. But this is primarily one of the things that you would think about when talking about the internal validity of some type of associational claim or study. Even if there is some third variable that is identified, it is not always a problem, as we will talk about on the next slide. So, it is problematic when subgroups have different characteristics, or when there are different groups that you could subdivide your sets of points on and they show a different style of relationship. So an example here, we talked earlier about having substantive conversations and how this was related to people's well-being. And we saw that there was an overall slight positive relationship in how many substantive conversations people had and their overall well-being. Now, what's happening here is it's showing ultimately fabricated data, but it's trying to illustrate the point of it could be that maybe deep conversations and well-being are not actually related directly to themselves, but maybe I'm seeing this relationship as a function of education levels being a third variable. And what I'm really saying here now is that maybe people higher on education just tend to have more substantive conversations and are higher on general levels of well-being than people with less education. And here you can kind of see how this would play out in real data. So here the green dots represent people who are in the high education bracket, and people with blue dots are represented as being in the lower educational bracket. And you can see that here those with green dots are higher in both sets of scores. They tend to have, if you sort of look here at the middle of the circle of green dots, they have more substantive conversations and are generally higher on well-being, while those in a lower educational bracket tend to have lower substantive conversations and are lower on scores of well-being. Now, if you think back to that earlier set of data that was shown for whether people met online or in person, and how ultimately that could be represented as a bar graph, and that bar graph ultimately showed the relationship. Here, if I was to draw a bar graph of both of these two things, I would see that those in the higher educated group are just higher on both of these things, and that ultimately the difference between these two groups, if you look at the line that forms from the middle of this group to that group, ultimately is what is giving rise to this artificial correlation between substantive correlations and well-being. Substantive conversations, excuse me. Whenever you have a case like this, where your third variable is actually explaining away the relationship you found, you would call the original relationship a spurious correlation or association. Third variables are not a problem when the sort of subgroups that are present in your data or that are divided considering this third variable that is put forward have consistent relationships with the original set of data. So here's just another set of data to show again the same relationship of deep conversations being related to overall well-being. And here the third variable being proposed is the amount of leisure time. So it could be that people who are high in amount of leisure time that they have more substantive conversations and tend to be higher on well-being, while people with not much leisure time tend to be lower on well-being and have less substantive conversations. You see those two divided here as the orange and blue dots. So the orange dots are people with high leisure time, the blue dots are the ones with low leisure time. But you can see even if you subdivide them, there is a positive relationship between substantive conversations and well-being for the high leisure group, and there is a roughly similar relationship for the low leisure time group for substantive conversations and overall well-being. So here, just because we have a third variable that does make sense, it doesn't necessarily take away from the actual findings, because just because we subdivide the data in this fashion, we see that our relationship that we originally found between substantive conversations and overall well-being remains consistent. Now, if I haven't mentioned this before, it is important that when putting forward third variables, it has to logically be related to both of the other variables. You can't just throw willy-nilly things in there like how many hamburgers did they eat on Tuesday, because ostensibly that might be related to a person's overall well-being, but maybe not so much to substantive conversations. Whereas leisure time does relate to both of these things. We tend to be happier when we have leisure time, and we tend to have more conversations in our free time. Just like education could also realistically be related to both of these variables. They do come up a fair amount, and just because a third variable is identified for a correlation and identified as being problematic, it is not often case or cause to simply throw out all of that data. Rather, this tends to lead us to then ask additional questions and run additional studies to allow us to disambiguate how this additional variable is actually related to the two that we were interested in, and upon studying those new relationships, what further questions and studies can be developed. Finally, some questions about external validity. So external validity just refers to how well the results from a study can be generalized to the population as a whole. We did talk about this a bunch previously, but it is important to remember that claims about external validity are largely based on how samples were actually selected. Was there random assignment of some kind that gave the majority of the members of the population an equal chance of being in the sample itself? The more and more skewed the sample, not in terms of actual statistical skew, but the more biased it was in terms of selecting, the less overall external validity is likely to be present in your study. Now, one thing to talk about here is moderator variables. Moderator variables are variables that change the relationship between two other variables. So the first place you're going to see this a lot is if you ever take a stats class where you will do a two-factor Anova. A bunch of those that you do will have moderator variables, such that two of the groups are going to be the same, and then two of the groups are all of a sudden going to become different, and it just depends on which category you're in. Now, again, you don't have to understand truly the ins and outs of all moderator variables. Much more important to just understand that they are variables that change the relationship between two other variables. So These oftentimes can inform our ideas of external validity because when we find a moderator variable, especially in association-based research, what we are saying is the relationship holds true for one group of people, but not for another group of people, because there the relationship is either non-existent or different than it is for this original group. And ultimately think of how that is related to external validity. We are saying with our moderator variable and finding it actually moderating the relationship, that there are two different classes of people for which the relationships are different. That means knowing information about only one of those automatically would not allow you to generalize just to the other group, and so it's theoretically possible, at least, that there is some lack in external validity, and this could now be above and beyond just how the sample was selected. Well, no, ultimately it still falls to that, because what could be moderating whatever happens to be our variable could be where one lives, what culture one comes from, what practices one follows, so on and so forth. And ultimately our sample, if it doesn't reflect this, will show that it is not able to accurately make predictions about the world at large. Okay, and that is the end of our lecture on bivariate correlational research. Thank you.